Welcome back. Projection of vectors. So I want to talk about this concept of projection of vectors. So here is a couple of vectors. I'm going to just bring them down for the moment. And what I'm going to do is I'm going to just kind of rotate this around just so that we're seeing that vector v1 almost being kind of like our horizontal. Now, projection of vectors basically has this concept of taking a vector, so in this case I'm going to take v2, and trying to project it down onto another vector, in this case projecting it onto v1. So it's almost like creating some kind of a shadow. And when we are going to be projecting the vector down, what we like to do is we like to project it down in such a way that it creates a 90-degree angle. So here, if I would drop this down and create basically a 90-degree angle right there, that particular projection, so this creates 90 degrees. This projection right there, so the shadow itself, going to put the shadow as kind of a shadow right there. This would be the vector projection of v2 onto v1. And the way that we make this notation, so this projection, we actually can write it out, and we typically utilize this notation. So projection of the vector v2, so because I'm using v2, projecting it onto the vector v1, and we put that as a subscript right there. That's the notation of it. Now, this indeed is a vector. So it has the same direction as v1, and its magnitude is really just that shadow that you are seeing. Now, that vector, so v2, it doesn't have to project out in such a way that the angle, as you can see there, actually is kind of less than 90 degrees, so that theta that you see within there. The angle can take on any angle. So as you can see here, so the various projections that I have, the projections could be, for example, well, they're just collinear. They're one which is on top of the other, and therefore the projection would actually be equal to just simply v2 vector, because it is collinear in the same direction. The same thing would happen if the angle was 180 degrees. Now, they're collinear, but they're in opposite directions. Now, what is interesting is that the case when we have an angle of 90 degrees in here, so for that case, what you're going to be running into is the case when the two vectors have a 90 degree, and you may recall if you do the dot product between two vectors that have a 90-degree angle between them, the dot product is 0. And that shouldn't surprise us in any way. And if we were trying to project a vector onto another vector, well, then what you would be running into is you're going to be running into a problem which would kind of look like this. So you would have your 90 degrees right here. So you have one vector, and then it's being projected onto the other one. And really, there would be no projection at all. Because if you would be thinking that it just drops down entirely, then that would just simply give us a mark of 0. I just want to remind you of what a unit vector is. Now, please don't forget that if you are given a unit vector, or at least if you're given a vector, it doesn't have to be a unit vector. So let's assume that we were given some vector v, and that particular vector maybe is, in some direction in this way. If you wanted to find the unit vector for this v, then what that means is that it's going to be the collinear vector, which is going to be in exactly the same direction as this vector. I'm going to change its color here. So make it, for example, red. And what makes it a unit vector is that its magnitude is equal to 1. So this is going to get scaled. Now, I don't know what that blue actually is, what that magnitude is, but let's assume that it's more than 1. So that means this one is going to get scaled down such that its magnitude this magnitude of this vector is going to be equal to 1. That's what makes it a unit vector. Now, how do we find that? Well, we find this vector by simply taking our original v vector and then dividing it by its magnitude. And when we do that, then we have created a unit vector. That is something that I have talked about in previous vector videos, but if you're watching this maybe without some of the other knowledge, then this is how you would define a unit vector in exactly the same direction as the original that you have. And whatever angle that it is or whatever direction that it's moving at is irrelevant. So this vector is going to take on exactly the same direction, but it's going to have a magnitude of 1. Now, the reason why we need that is because when we're going to be doing projections, the projection is going to be on top of another vector. So the projection itself is going to have the same direction, but of course it could possibly have a different magnitude. So now let's dive into these projections and then how to find them. So I'm going to take the easier case first to discuss, which is this one. So the assumption here is that given two vectors, what I have is I have that their angle in between them is either somewhere between 0 and 90. So it's not 0 and 90, so I've talked about that case, but it could possibly be something like I have drawn over here. So I'm going to duplicate this, copy it, and bring it down just so that we have a visual. So within here you can see that theta is clearly less than 90, but it is greater than 0. And now this does not mean that that vector v1 is actually horizontal. It doesn't matter in which direction it is. You know, I can certainly move it. Okay, for example, shift it a little bit just so that you don't think it's horizontal. And we're still going to be interested in that gray vector, in that projection that we have. So how do we find this projection? Well, the projection is actually not that bad to be able to find it if you remember that you can always find what the actual, if you have the angle, what that actual magnitude is, because of the fact that you're projecting out onto and you have a 90-degree angle. So what you create here, you basically create a triangle right there where you have your vector v2, which is the one being projected. This one is your hypotenuse to the triangle between these two sides. And because we know what this angle is, then it is actually very easy for us to be able to find what this shadow magnitude is. That shadow magnitude is nothing else but simply the actual magnitude of v2 vector, so whatever that is, and then it is being multiplied by the cos of the angle in between. And that's going to be the actual shadow. And that's not surprising, right? So let me, call, for example, that particular shadow. I'm going to just put P in here, just for projection, down. So that particular projection, I'm going to put, for example, the absolute values. That's how we would find it, right? Because cos of the angle is nothing else but adjacent over hypotenuse. So if you're thinking about this, well, this is my adjacent. My hypotenuse is this right there. And adjacent over hypotenuse is just cos theta. And of course, if you isolate for the magnitude of that P, that projection, which is going to be that V, or that V2, I apologize, is going to go up on top there, and you're going to get exactly this. So that is the magnitude of your projection. So your projection, which I'm going to be calling P, is equal to this. But this just gives us the projection. Now, if you want to know what that shadow vector is, then I can use exactly what I just did up above here. I can find out what the unit vector is in the direction of that projection, so in the direction of that shadow. And that is very easy for me to do. So that's this right here. And if I have the unit vector and I have the actual magnitude, well, the magnitude times the unit vector is going to identify what that projection actually is. So bringing those things together, my unit vector itself in this direction, so this particular unit vector in the direction of that is nothing else but just v1, right? So that you have right there, and it is being divided by the magnitude of v1, and this is just the unit vector in that direction. So I have the actual unit vector, I have the magnitude, and if I combine the two, so if I multiply the unit vector by the magnitude, I'm going to have that projection. And that's actually how we define what the projection of a vector is. So in completeness, you can say that the projection of a vector, so v2 in this case, onto another vector, v1, is equal to the magnitude of that projection, so it's going to be the magnitude that I found there, multiplied by the actual unit vector of the v1 vector. Well, this we have as, so this is v2 magnitude multiplied by the cos theta, so the angle in between the two, multiplied by the v1 vector divided by the magnitude of v1. So it looks complicated, but again, this is nothing else but simply the magnitude multiplied by the unit vector. And that is it. That is your projection that you have. So that's that shadow that we were actually finding out what that is. Now, sometimes you may not know the angle, but you can always find the angle. So even if you have the vectors given in, for instance, Cartesian form, so Cartesian vectors, then you can find out what that angle is. Now, I did a video on that. I can put it back up there, but I can also illustrate it through an example. So let's take a look how this would work. So let's imagine that I have vectors, okay? So, and I'm going to try to make it visual just so that you can see this. And it doesn't have to be in the first quadrant, but I'll make it maybe in the first quadrant just for kind of completeness, okay, so that you can see it. So let's say I have one vector. Maybe this is my one vector over here. So that vector, and we can count it up. So that's 1, 2, 3, 4, 5. So this is the vector 5, 1. This is in Cartesian coordinates. I have another vector, so let's create another vector over here. So maybe this one right there. Let's make it a little bit nicer. So I have another vector right there, and this vector is 1, 2, 3, and 1, 2, 3. So this is my other vector. And there we go. And now if I want to be able to find the projection here, then what I have to do is I have to find the projection out. So this is going to be dropped down, so basically at a 90 degree, and I have to find out what this angle here is, right, between the two vectors, okay, and this is going to get dropped down, okay, such that it creates basically some 90 degree angle in here, and I can proceed, okay, and go ahead and find that out, right, so I can do this directly. Now, if I do have these Cartesian, okay, coordinates within here, I can actually play around and then find out what am I discussing, okay, in terms of trying to find, okay, that projection and what that vector is. So I just want to be able to do this for you. So there is, an actual brute way force of trying to do this, to find out that angle first, do this actual calculations, but I just want to show you, okay, that you can take this right here, so you can take this and we can actually simplify it a little bit. So I'm going to take this throughout and I'm going to just make a copy out of it so that I can show you that you can do it with dot products as well. So for instance, if you have vectors, okay, and this is, so I'm assuming that this one right here, for instance, is v2, okay, that's my vector v2, and then this one right here is my v1, and I want to be able to find what that projection vector is. The magnitude, okay, is simply v2 times cos theta, but I don't know what that theta is, at least not for the moment. So here, take a look at what happens here. Now this is going to be from right here. I just want to take this and then multiply it out. So I'm going to be multiplying this out by the magnitude of v1, and I'm going to be dividing it by the magnitude of v1. So really I'm just multiplying by 1 because the magnitude of 1 divided by the other one is 1, so it doesn't change anything. And now if I'm going to be dropping this in here, so I'm going to duplicate, okay, so I'm doing that. Now, look what happens here, that what you're going to get out of here, so if I do this right there, then I'm going to get, this is v1 magnitude times v2 magnitude times cos theta in between. I'm going to take this right here because it's just division, and I'm going to shift it over, so it's going to be multiplied by, and now all of this right there, this one, okay, duplicate it, bring it back, and notice, so what happens is, because I have one of these here, and it is being multiplied, notice I have the other one over here, so v1 magnitude times v1 magnitude, so this right here is going to become squared. That's what I have in here. And so from this, you'll notice that I have the following, that this is nothing else, so this right here, this is by the definition of the dot product, this is just v1 dot product with v2, okay, so that's what I have in there. So that's the actual result there. And then, okay, what I'm doing is I am now multiplying, so this right here, so what I see right here is v1, so the magnitude of this, well, that is, okay, so I'm going to take this out over here, and this is nothing else but just v1 dotted with itself, with v1, so that's the dot product in between that. Those are just the properties. And then it's being multiplied by, v1 vector. Now, why would I do this, you might ask? So why would I want to be able to, change my projection to this? Well, the reason is that if I am dealing with Cartesian, so something like this, Cartesian vectors, notice in this case, I will no longer have to find what that cos theta is. I don't really need that at all because I just have the dot product in between the two, and then I am multiplying by the v1 vector. That's it. This right here, these two dot products, well, I can definitely do that. That's without any problems. And then I can just multiply by v1, and this is the projection. So you can either write the projection, okay, in this format right there, so that's one way of doing it, or you can do it by just what I have shown, right, through that multiplication. So these two are equivalent. So I'm going to just write this right here. I'm going to shift this over right there. These two are identical. All right. So if you have maybe geometric vectors and then you know this theta, so if you know the theta, go ahead. You can right away find out what the projection is, and then you can find out what the unit vector is. If you just have Cartesian vectors, then I would suggest that maybe, you use this, because in this way you don't have to take the extra step of finding cos theta, although of course you can. Depends on your time. So let's illustrate this. So I'm going to take this is 3, 3 and 5, 1. So I have 3, 3 and 5, 1 as my vectors. So this is going to be 5, 1 dotted with, okay, 3, 3, which was my v2. Okay, it's going to be divided by, and this is going to be 5, 1 dotted with itself, so 5, 1, right there, and then the actual vector, okay, is still 5, 1. So to find this out, well, this is going to be 5 times 3, which is 15, and then 15 plus 1 times 3, so it's going to be 18. So I have 18 all over, and then this is going to be 25 plus 1, which is 26, right there. I can certainly simplify this if I wanted to. So divided by 2 is going to be 9, and I guess 13, right? Because 2 goes into both of these. So I can divide by 2, divide by 2. And then I have my vector right there. Now this is a constant right here. So I can bring it inside. So I can bring it inside of here, and then I can find out that, okay, well, 9 times 5 is 45, all over 13. And then 9 times the 1, well, that's just 9. So it's going to be this. And there you go. This is now the shadow that this would cast. So right here, okay, if you would be doing this, that you have now found this vector right there. That is the projection of V2 onto V1. And that's how you would actually find it. Okay? So there you have it. Now, sometimes, you might think, well, all right, so this is great. And by the way, so this will definitely work for the fact that when you are dealing with an angle between 0 and 90, now, you might say, well, this was nice. I mean, I could see that this is definitely less than 90 because this is visual. But if someone just gives me 2 vectors and I don't have a graphical representation, how do I know it's less than 90, and how do I know that the formulas are going to be aligning? So we obviously would want to be comfortable in using these formulas also for the cases where the angle is greater than 90, so it's between 90 and 180. So let's do that next and try to talk about that particular example. All right, so here is the case when we are between 90 and 180. So notice you have your V2, and we're going to try to project it onto V1. Now the first objection that you might have is, well, it's not going to project at all, because V1 is kind of moving to the upper right-hand corner and V2 is moving to the upper left-hand corner, so the projection won't really matter. Now, what I would want you to visualize is when you are dealing, okay, with these particular vectors, when we're talking about projection, when it's less than 90, then it makes sense. It just drops a direct shadow. Now, in the case where the angle is bigger than 90, then what we are actually referring to, so here, is that you can imagine that you have, it's almost like I'm going to do a dotted line in exactly the same kind of line as my vector V1. So the shadow that we are now referring to for this case is this shadow is being dropped down. So I'm going to just kind of drop this down. Okay, and let's create a 90 degrees there. I mean, as well as I can. So what we are referring to, that shadow is now being dropped on the opposite side. So it's still collinear with V1, but it is in the opposite direction. So if we were thinking about trying to create our projection now, then our projection is going to be basically this, right? That's what our projection is going to be. It's still going to be in the direction of V1, but now in the opposite direction, right? So that's what happens. Now, if we're going to be defining the projection in this way, so let's see what this would be. Now, let's take a look. So we know from the case when we were dealing between 0 and 90 degrees, that our magnitude was simply just the actual magnitude of V2 multiplied by the cos of that angle. Now, in our case right here, so if you're going to be doing this, well, what happens is, really, we're looking at this angle right there. which is, so if you remember, so this is 180 degrees minus theta. So that's the angle right there. So I'm going to put this as angle theta prime. So that's my angle there. And if I want to know my projection, okay, of that V2, then my magnitude, it's still going to be, so now it's going to be V2, so this right here, okay, multiplied by the cos, okay, of that 180 minus the theta. Now, you may recall that taking the cos of 180 minus theta, that is exactly the same thing. So this is just from trig identity. So this is the same thing as saying negative cos theta. That's all that is. And that indeed is true. So therefore, what you see right here, so that particular magnitude is nothing else but simply, so that negative I'm going to drop in front. So this is the magnitude of this, and then it's going to be of cos theta. That is the magnitude. Now, that negative right here, so that is the magnitude of this. And now, we still have to take this and then multiply it by the unit vector. Now, that unit vector, so notice right here, we're no longer going in this direction. We're going in the opposite direction. Well, we know that the unit vector was V1 divided by the magnitude of V1, but this had the same direction as V1. But our unit vector now is in the opposite direction, so we do have to have a negative in front. So it's the opposite. And if you do that, so if you now multiply this by the negative of V1 divided by the magnitude of this, well, what you will find is that the negative and the negative will cancel, and you're back to exactly the same thing, which means that even if the angle is different, then you are still going to be dealing with the same projection, so the same shadow calculation that you would have. This would be right there. So that's exactly the same as what we had over here. So if you have noticed, so this is exactly this, exactly the same, which means it equals to this as well. So in total, it doesn't matter actually if the angle is between the 0 to 90 or if it is between 90 to 180, you're going to get the same projection out. So that's what we would have in there. So no matter what, you can treat them exactly the same, okay, for those. So those are the actual projections. You know, you can find it out. I'm sure that some people will just simply memorize the formulas. But if you are thinking about the actual magnitude multiplied by the unit vector, then in those cases, you will be able to see, okay, that it is simply, okay, the projection of one onto the other. Now, I wanted to give you one more thing. Now, because sometimes you're only interested in the magnitudes themselves, right? So you don't necessarily want to be able to know what the vector is of the shadow. Maybe you're only interested in the actual magnitude, okay, as a whole without the direction. So in those cases, you know, you do have to be careful, because the magnitude, for instance, between, so if you're going to be taking the magnitude only, that magnitude indeed is going to take on a negative sign, because if you're between 90 and 180, it is in the opposite. So the magnitude is actually negative of the V2, okay, multiplied by cos theta. That's what you will find. Right? The negatives canceled because here the projection, this also was negative. That's why our formula looks the same. but please don't think that the magnitude is this. The magnitude is that, but it's the negative of it. And then the unit vector, okay, is not this, it's the negative of this, and then the two negatives cancel. So that's what happens. So if you're thinking about magnitudes only, and you're not interested in anything else, then for angles between, so as you are between 0 and 90, then the magnitude itself, if you're calculating it, it would be this. But if you're going to be dealing with angles between 90 and 180, then the magnitude is the negative of that. So just be careful if you're only interested in the magnitude of the projection. All right, but if you're interested in the entire thing, lucky for us, those negatives canceled, and we only have to remember really just one formula, which is that. All right, and you saw that I did it with one vector, and you can do it with any other vectors that you like. Now, what is interesting is if you do take the magnitude, so this is for this is just a side note. In case of the fact that you are dealing with Cartesian vectors, as you saw, Cartesian vectors are not going to tell you what the angle is. So in those instances, you know, you certainly can just be careful. So I'm going to just duplicate it. Okay, so notice that you can simplify this by what I did with the trick over there, by multiplying by V1, so the magnitude, and then dividing by V1, okay, as the magnitude of this. Now, what that does is it doesn't change anything for us, but this is going to be equal to V1 dotted with V2 divided by just simply the magnitude of V1. So that is the same. And if you don't feel like finding out what this cos theta is between the two vectors, if you're given it in Cartesian vector form, then you can use this right here, okay, as your magnitude. And then if you have an angle which is between 90 and 180, then as you can see here, so this, okay, it's going to be the same thing as this, but you got to put a negative, okay? So a negative would come up here, okay, if you're dealing with that case. So if you're unsure, then just find your cos theta, right? So your cos theta can be found. I pointed out how to find the angle between two vectors. You know, I showed you a link, so you can always do that. All right, so that is the projection. So the ultimate projection is we're trying to find the casted shadow vector between the vectors. So we're basically just projecting out. Okay, it's like we're shining a light on top of it, right on top, and then it's going to create a shadow. So either to the left or to the right, depending what that angle is. And that projection is nicely defined right here for us. Okay, in case you remember, I always think about just magnitude multiplied by unit vector. And then if I want, okay, I can certainly change it, okay, to this form if necessary. All right, thank you for watching. I hope that you made some notes. You can go through them. Okay, I gave you one example. I'm sure that you can try many more examples, okay, on this. And I'll do some applications with regards to this as well. All right, take care, everybody. Bye-bye.